Okay, so we're going to be doing error detection and error correction systems. And the first form of error detection that we'll use is the parity bit. So this is the oldest form and the most commonly used. So first one is called parity bit. Parity bit error detection system. So how does it work? Very, very simple. It's old, it's been around for a while. And it's probably still the most used one, because not because it's great, but because it's in the system already. And it's cheaper to leave it in the system than to get rid of it. So how does it work? All information stored, this has been around since information was stored in tapes and paper as well, but it doesn't matter where it's stored now. Whenever you have information, remember one thing is that all information is stored or transmitted in the forms of ones and zeros. So everything stored on your hard disk, whether it's a picture or video or image or text, it's actually in its basic format, it's just lots of ones and zeros. And if it's on the hard disk, it's a magnetic charge to represent one, or lack of it to represent zero, or something like that. But we read it as ones and zeros. So a file can be just a lot of ones and zeros, and so on. So it could be like that. And if you want to send this file somewhere and receive it at the other end, how do you know if one of the bits flip from 1 to 0 or 0 to 1? So they decided, okay, let's use the existing system that was there. In the older days, anytime they stored information, sometimes it changes on the hard disk. So they introduced systems to say every time you read a document from the hard disk or from the storage, the tape, we do a check on it immediately. Is it correct, or has it been changed? So how do we do that? They say every time you want to store information, or now every time you want to transmit information, we'll add an extra bit. We'll call it the parity bit. There are a few kind of systems that are in standard use, but we just take one of them. One of them is the 7-bit. We just take 7-bit. There are systems that take 8 bits and add a 9th bit. There are systems that take 7 bits and add 1 bit. So it doesn't matter which one, but we're going to use one that now we take 7 bits and we insert an extra bit. So in this particular case, we count, for example, this is what we're going to send. This is the first bit. Imagine this is the out, the transmitter is going in that direction. So we count 1, 2, 3, 4, 5, 6, 7, and we're going to insert 1 bit, an extra bit, 1 or a 0. We don't know yet. So we'll either put a 1 or a 0 here, and so on here. And then 1, 2, 3, 4, 5, 6, 7, and we add another bit here. 1, 2, 3, 4, 5, 6, 7, and we're going to add another bit here. So imagine that's the bit we're going to add. So now all we need to do now decide is that we're going to add a 1 or a 0. So now again, the parity bit has two kind of systems, and the systems are either even or odd. It's called odd or even parity systems. Let me just make sure. Okay, so there's a system called the odd parity, and there's a system called even parity. So the guys, the receiver and the sender, must agree, are we going to be using odd or even? It doesn't matter. So let's use even in our case. It doesn't matter, but let's go for even. Excuse me. What does even mean? The even means in every byte, there has to be, if you count the number of ones, there'll be an odd number. Right, so if you count 1, 2, 3, 4, 5, this one has 5. No, it can't have 5, it must have 6. 6 is an even number, so that's an even number. And that decides what our new bit should be. So for example, let's take just the first byte here. I'm gonna reverse the bytes. Just, I'm going to bring it down. It's 11011101. In fact, the bits are always added at the end. I'm going to add them at this end, okay? So it doesn't matter. So this bit is not part of the user information. So these are 7 bits, 1, 2, 3, 4, 5, 6, 7. We're going to add our parity bit here. And we count how many bits there are that have the value 1, 1, 2, 3, 4, 5. Then we must make them 6 by adding a 1 here. Right. Let's say let's just say the next byte is 00000011. We're going to add a 1 or a 0 here. What shall we add there? 0, because here you count how many ones? 2. You can't make them 3, so we'll leave them as 2. So we add a 0. So these bits are extra information. This is redundant information. If you heard about redundant information, we were doing switching virtual circuits and datagram. Datagram sends a big header. All that header is redundant information. What's redundant information? Anybody can give me a quick definition of redundant information?
Information which is not needed.
Any information that we send with the data that's not part of the data. And it has to be removed at the other end. And we always try to minimize it, right? That's redundant information. So now for this parity system, every byte or every 7 bits we add 1 bit. Imagine the next, for example, this one here, 1, 2, 3. What's the next bit here, the parity bit? 1. Thank you, yeah, I didn't see you. I heard the 1, but you didn't move at all. I said, how did you do it? Okay, so and so on. You keep doing that with every byte. If you're storing the information on a file, that's the way they used to do it. They start reading and sending the information storing it onto a tape or a disk. Even on your hard disk right now, every file stored, it actually has a parity bit in every byte. And when you read it, the operating system in the background reads it and counts the number of bits and removes the extra bit. And if there's a problem, it'll tell you parity error. You have a parity error. So if you ever get a message called parity error, that's what it means. It means one of the bits in your file is flipped. Either one turns 0 or 0, 1, or maybe 2 bits, we don't know. But there's an error in your file. That's what a parity error is. So all information. So now if we're sending a file through communication, through a network, and we break it into small packets, and we take the packet and the header, and we start everything we transmit, we count 7 bits, and we insert 1 more bit. Count 7 bits, and we insert another bit. And the receiver, when the receiver receives them, he'll do the opposite. He'll start counting to 8 bits, make sure they are even. And if it's correct, get rid of the parity bit and keep storing that information or sending that information. So the parity bit is only used, in our case, during transmission. Just before we send, we put the bits. The receiver uses the bits to check the correctness. And once they're happy, they can remove the bits and back to the data. So if the receiver receives this long string of bytes, then it has to get rid of those. Those are called parity bits. All right. Now, let me give you this example. 2, 4, 6, 8, 10, 11, 12, 13, 14. Is there an error here or there is not? And we sent those 2 bytes. Is there an error there? We sent them using even parity bit. Can you check those and tell me if there are any errors in there? Or can you not? Who's next? How does the reader check? Is there an error? Is there an error here? Can you check? As a receiver, I've just sent you this information. That information contains the data and the parity already. Come on, guys, on that end. Do you want to tell me? Is there an error in there or not? Maybe still people don't understand the question. Pardon?
Is it even or odd parity?
We used even parity. The sender sent us data using even parity, and we received it, and here it is. There is an error? Why? How do you know there is an error? Okay, because you take 8 bits, 2, 4, 6, 8, up to this point. Let me do it here so you can see. Right, now, is there an error? Okay, hold on, this is 1 byte, 1, 2, 4, 6, 8. Up to this point, it's a byte. From this point, 2, 4, 6, hold on, 2, 4, 6, 8. Sorry, so now we have 8 bits, 8 bits. That's what we received. We sent it, the sender, he said, we sent it using even parity. What does that mean, even parity? It means every byte must contain an even number of bits that have the value 1. So now let's count. 1, 2, 3, 4, 5, 6. That's okay. There's no error. This one, 1, 2, 3, 4, 5, 6. There's no error. They both have 6. They could have 2 and 0 and 6 ones in each byte. As long as it's even and the 0 is considered even. Okay, so that's how it works. Very simple, very efficient, and very beautiful system. And it's been around for God knows how long. Since computers started, they started using this system. And it's almost in every system, in every database, it's there. They can't, it's even so expensive to get rid of it, so they said leave it. Yeah?
It would be useless if there is 2 errors in 1 bit.
Yeah, I'll get to that. Okay, you're ahead of me there. Give me a few seconds. Okay, yeah, that's correct. So, all right, this is how it works. It's simple, it's nice. Right. Now, let's say I'm going to send this information again. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 2, 4, 6, 2, 4, 6, 7. 2, 4, 6, 7. Right, and 1, 2, 3, 4, 2, 3, 7. So here's 7 pieces of information. You are a sender. We're going to do odd parity this time. Tell me what parity bits you add in there. The first byte. What would the first byte? This is now odd parity. 1, 2, 3, 4, 5, 6. So we add 1, so now it becomes, that's the parity bit, and the total of bits is 7. Right, the next one. 1, 2, 3, 4, 5, 6, 7. 0. Those are 7. And the next one? 0, so 1. This is odd, this is good, odd, and that's what the sender sent. Right, now, Abdurrahman, don't look, close your eyes. I'm going to flip one of the bits, right? I want to see if you can tell me, is there an error in this system or not?
There is, now it's even.
Yeah, where? Which byte? You don't have to count, you don't count all the bytes and get the total, 1 byte individually. So where is the error? In which byte? This one here, 1, 2, 3, 4, 5, 6, 7. That's odd, right? And this one, 1, 2, 3, 4, 5, 6, 7. That's odd as well. What about this one? 1, 2, 2. Oh, 2 is even. That's where you say, there's an error. But you delete the whole file or frame or packet or whatever it is. You don't just say, okay, this byte. You don't know which byte, you know which byte, but you don't know which bit. But what we do is get rid of the entire file. Now, who wants to take the next little problem? Now, okay, so here's another issue. 2, 3, 4, 5, 6, 7. One of the problems they found in this is that sometimes you get an error and you cannot discover it. Not just one error. She suggested sometimes you get 2 bits. Okay, now if this bit changes to 0, we discover it. If we count, the receiver now counts 1, 2, 3, 4, 5, 6. Say, 6, it should be odd. 6 is not an odd number, it's an even, then there is an error. Right, but what if this bit also changed into a 0? So now we have 2 errors. So the receiver counts, how many ones do we have? 1, 2, 3, 4, 5. Let's say 5 is good, it's an odd number, there's no error. In fact, there are 2 errors. So this parity system doesn't always work. if you get 2 errors in the same byte, they cannot be discovered. Or if you get 4 errors as well, it cannot be discovered. So if this bit also changed and that bit changed, and you count 1, 2, 3, 3 is also an odd number, or 6. So if you get 2 bits flip, or 4 or 6, then they cannot be discovered. So only odd number of bits. If they flip, we can discover them. That's the problem with this system. So if you ask, what's the problem with this system? It doesn't discover all errors. Are you with me? It only discovers the odd bits, the odd number of bits if they change. But if you, in the same byte, now remember, if 1 bit changes here, let's get this back to normality. This is another 1 here, right? So it's 1, 2, 3, and that's 3 odd, right? But no error. But now I'm gonna change this to an error. This is an error, 0, and this is an error. These are 2 bits changed. Do you think we'll discover them?
Yes.
Yeah, we'll discover them because they're not in the same byte. If the 2 bits that change in the same byte, so be careful, it's important. If you're asked, what errors cannot be discovered in parity system? And you say, if there are 2 bits or 4-bit error, that's not a good answer. In the same byte. You say it's in the same, if in the same byte you get 2 bits or 4 bits, then that's a problem. Right, so that's one error detection system. It's simple to use, but it has, it's not very effective. It doesn't discover all errors. Now, when we evaluate error detection systems, we evaluate them, say, in 2 points. First, does it discover the errors, all the errors, or not? The second one, how fast it is. And the third one, how much redundant data do you send, a lot or a little? So how about redundant data here? Does it send a lot of redundant data or very little redundant data? Very little. Yeah. It only sends 1 bit. 1 bit in every byte. Is that little?
It's 1 to 7.
1 bit in every byte. That means 1/8. 1 to 7 in ratio of your data is redundant. That's a huge amount. Okay, when you are only sending 1 byte or 2 or 10 bytes, okay. But if you're sending millions of bytes, then there are going to be millions of bits that are sent. So in fact, in ratio, 1 errors, 8 to 1 or 1 to 8. 1 is parity bits, and 8 is the total data. No, it's not 1 to 8, 1 to 7, because the 7 would be data and 1 bit would be error. So 1 to 7 is a very high ratio. In fact, 1 in 8 bits is parity. So if you're sending 8 million bits, 1 million of them is actually redundant data. And that's not little extra, that's big redundant data, huge. So it's not really a great system to use, at least for those 2 reasons. What are the 2 reasons that give you issues, problems with parity bit error detection? Okay. Okay. Anything else? What's the disadvantage of parity systems? What's the problem with parity error detection systems? Yeah?
Sometimes the database is too much.
It does not discover all errors, and it sends a lot of redundant data. These are the 2 major problems with it. What kind of problems it cannot discover?
We have 2
bits in the frame, it will not discover it, right? Wrong. Wrong.
If there are changes in different bytes,
If 2 or 4 or 6 bits flip in the frame or in the packet?
In the same byte.
in the same byte. Yeah, you didn't say
I was
same
gonna
byte.
say,
No, you were going to say, but you didn't say it. You don't get a mark. That answer you gave would not get you the mark. If you say, oh, it doesn't discover 2 bits or 4 bits or 6 bits, and you stop, you get some mark. If you can say in the same frame, you get 0, or the same packet or the same file. In every byte, it has to be in separate byte, 2, 4, or 6. Right, so that's really parity bit system. You should know it. You should already know this. Now, we go to the improvement that they did. With little change, they were able to fix a lot of these little parity bit errors. They call this, the next one is the block parity. Block parity system. So the block parity still uses parity as well, but it uses it in 2 dimensions, rows and columns. So for example, if we take the frame or the packet you're sending, maybe 3,000 bytes, let's put them one on top of the other. Let's say here's a byte, 2, 4, 5, 6, 7, right? And then 1, 2, 3, 4, 5, 6, 7. And then 1, 2, 3, 4, 5, 6, 7. And then 1, 2, 3, 4, 5, 6, 7. Here it is. And 1, 2, 3, 4, 5, 6, 7. Here's the entire frame. Now, they said, okay, let's first agree, odd or even. Odd parity. Let's go for odd parity this time, okay? Odd. So the sender wants to use odd parity. What does that mean? That means the sender will insert the parity bit to ensure every byte must have an odd number of ones. And the receiver will check, make sure every byte has the odd number of ones, and then get rid of that extra. If everything is good, get rid of the parity bit. Now, with the block, we have to do it this way, horizontally for every byte, but we also have to do it vertically for every column, for the 7 columns. Right, let's start and do this. Who wants to work this out for me? Yeah. I don't know. Who has not participated? Can't remember your name, but hey, tell me, what, you are the sender now, you want to add a parity bit here. What parity bit will you add in each, at the end of every byte? This is odd parity. 1, the next one. 0, why 0? Because you counted these ones, they're already 5. You don't want to make them 6, you leave them 5. Okay, next one, there are 7 bits. Pardon? 0, yeah, okay. The next one, 4. 0, perfect. So we add parity bit at the end of every byte. Now, this system, the new system, also count downward in every column and add a parity bit. Do you want to have a go at this? Yeah, tell me, what bit will I add here? 0, why? 1, 2, 3. So we want to leave it as odd, 0. Okay. 0. Sorry, yeah. 1, 2, 3, 0, yeah. They're all zeros. 1, 2, 3. I'll put it there. Now the last 2 columns, or the last column. 1, 2, 3, 4, 5. Oh. And even the parity, you can do the parity if you like. 1, 2, 1. Okay. So that's what the sender does. It does 2. And remember, when the computer is this fast or slow, it's actually extremely fast. One of the fastest algorithms or ways of processing, because computers are not good at counting or adding and writing the number at the end. What they're good is at ANDing and ORing. The logical operations are so fast. Computers are fastest when they're doing logical operations. They don't add. They're not good at adding or subtracting or they're even worse at dividing or multiplying. But what they're good at, ANDing and ORing. So what they do here is they just keep take the bits here and this with this and leave the result at the end. That's all they do. And that's extremely fast for computers. So anytime you find a program that does anding and oring or comparing anything logical operations, it's very fast. If it starts going into dividing and, you know, subtracting and all that, it's slow. So this has the advantage, it's that it's extremely fast. But it, of course, you know that we have an issue with it. It doesn't discover all errors, and it has a high rate of redundant data. Now, this is what we send now. This is the frame or the packet that we send or the message. Now you're a receiver. Now I'm going to put an error. Remember the problem with the first one. Let's just have one error to see that it already works. Now I'm going to switch one of these bits. Yeah, don't look at the screen now. Right. Tell me which byte has an error. Yeah, which byte here has an error? You're a receiver, you just received this. One of them has an error. Which one? How do you know? You have to count the number of ones here. 3 in the top one. 1, 2, 3, 4, 5. That's 5 here. 1, 2, 3, 4, 5, 6. That's 6 there. 1, 2, 3, 4, 5. That's another 5. 1, 1. So which one has the error? The third one, the one with the even. So it works. We know that it works. Right. Now, look away again. I'll fix this. Where was it? Now, this one. So I'll fix it. There it is. It's fixed now, right? Now, I'm going to put 2 errors or see if they can be discovered. For example, we get to this one. I'll just put the underline. So these are the 2 I'm going to change. So I'm changing this and I'm changing this. 2 bits in the same byte. Now, we couldn't discover this before. Now, can we discover it? Who wants to take this? Yeah, go on, take it.
Check vertical, you should check vertical.
Now, there's an error there. Can you discover this? How do we discover that?
Check it vertically.
Right, so if we count horizontally, we say 1, 2, 3, it doesn't, we can't see it. We can't see the error if we count horizontally because there are 3, and 3 is an odd number. But now, if we count vertically, 1, 2, 3, that's odd, that's...
That's because
Oh,
you changed in the third one.
This should have been 1, right?
No, you changed in the third one.
Okay, we changed this one.
Yeah.
All right, okay. Yeah, so all right, we started discovering. So let's go to this column. 1, 2, oh, and that's even number, and we discovered. So if we miss any horizontally 2 or 4 or 6 bits in 1 byte, we'll discover it vertically. So this solves the problem at minimum. What's extra? We have a bit of extra redundant data, but only 1 byte at the very end. So it's not a huge amount. If a packet now is about 3,000 bytes, if we add 1 byte at the end, it's not a big change from the previous one. It's still bad because it has an extra bit at every byte. But when we compare block parity with normal parity, there's very little difference in processing time or redundant data. So it works, it fixes the problems all the time with minimum extra amount of data. Is that right? Now, let me put those. Which ones did we flip? This one and that one? Okay, let's change them back. Let's put them back to 1s. That's 1 and that's a 1. Yeah? Just 1, is it? Okay, that's a 0, that's a 1. So now if we count 1, that's odd and that's odd. Yeah, that's perfect, yeah. No, the third one is not. The third one should have been 1 as well. Yeah, okay, I'm gonna make this 1. That's the 1. Right, imagine now we sent this. How many 1s are there? 3, 2, 4, 6, 7. That's odd. That's 5. That's 1. And that's okay. We don't need to count that. At the bottom, 3, 1, 1, 3. Oh, 2 is not good.
Yeah,
because we flipped that. Okay. Okay, let me fix this one here by leave that 2, and I'm going to make this one 1. And then it should be this one here. Oh, flipping hell. Okay. So now, this is the same frame again, sent by the sender. But let me change those two. Remember, okay, let me change this to 1 and this to 1. Now let me change this to 0. It was 1, turn it into 0, and this 0 into 1. So I changed 2 in this line and 2 in this line. 2 in this line, will they be discovered? 1, 2, 3, 4, 5. No, we cannot discover. You say this is a good one. 2 bits are gone. Okay, this one here, 1, 2, 3, 4, 5. We say there's no problem. There's 5, and I did change 2 bits. Right, these are the 2 bits I've changed here, and these are the 2 bits I flipped here. Right, so we have them underlined just so you'd know which bits. Now, can we discover them vertically? Well, yeah, we should. So 1, 2, 3. That shouldn't be there at all. This one here, we should, I don't know. The point is that we cannot, let me give you an easier example. This has just gone too messy. Okay, so it's 1, 1, 1, 1, 4 ones and 4 zeros. This is 1. That's an even, that's 5. Okay, and 0, 0, 0, 1, 1, 1, 1, 2, 4, 5. That's another, it shouldn't be 5, but okay. And then 1, 0, 0, 0, 0, 0, 0, 0. That's 1. Right. Now, what I'm going to do here is change 4 bits and see if it works. I'm going to change this bit and this bit. So that's going to go into 1. This is 0, and this goes into 1. And same with this one. I'll turn this into 1, and I turn this into 1. So we change 4 bits. So let's count this way. 1, 2, 3, 4, 5. No error. And here, 1, 2, 3. No error. So horizontally, we do not discover them. Let's go vertically. We never did the vertical bit. One more time, and last time this time. 1, 1, 1, 1, 0, 0, 1, 1. How are we doing on time?
2 more minutes.
2 more minutes. Oh, come on. Okay, now what's the vertical bits? This is odds. 1, 0, 0, 1, 0, 0, 1, 1. Right?
First line, even number.
No, odd. 1, 2, 3.
No, line, no.
1, 2, 3, 4, 5, 6. Okay, I'll turn this into a 0, and that also here will turn into a 0. Okay, thank you. So we have 5 this way, 5 this way, 1 that way. Downward, it's 3 and 1.
1, 3, 1, 3.
Right, and remember, these are parity, the parity bits here, and these are the parity bits that will need to be removed if everything is good. Now, let's change this bit into a 0, and this bit into a 1, and say this bit into a 1, and this bit into a 1. So I flipped 4 bits. That one, and those 2. So if you count horizontally, 1, 2, 3, 4, 5. Still no problem here. 1, 2, 3 is no problem. Let's count vertically. This one here, 1. Perfect. and 1, 2, 3, and therefore it's perfect as well. So there's the 3 here, which is perfect. So this way we did not discover any error. So this system works except in one situation. If, an example, any 2 bits on 2 different bytes and on the same 2 columns, they flip, then they cannot be discovered. Just to think of that, if you have a box, imagine if I have a rectangle that goes this way. Now, the corners of this rectangle, those 4 bits, if they flip, they will not be discovered. Any box that goes from, the corners are at bits. Imagine if we change this bit and that bit, and this bit and that bit, those 4 bits will not be discovered. So this is the problem with this system. If you put a table of bits, if you have the frame or the packet in like a tabular format like this, and you draw any box anywhere on the bits, and you flip those 4 bits, if they change, it's unlikely to happen, but if it does, you will not discover the error. So that's another problem with the block parity. So block parity is better, except in this single situation where you have 4 bits. Is our time up?
Yes.
Okay. I'll see you next week and we'll finish this. Thank you, guys. I'll put those notes on Moodle, so have a look at them.